we have seen that our coupling coefficient decrease as the air gap increases. So in the similar fashion, your mutual inductance will also vary. As the air gap increases, your mutual inductance will decrease because the coupling uh, between the primary and secondary is changing, right? But you will not observe much variation in your self inductance. Fine. So from here, you can also analyze your induced voltage in the winding. Sorry, we will take magnitude here, right? Or else this will come. So select from function, select magnitude option, new report. Okay. So can you see you are getting certain 2 kV kind of voltage around, across the coil. So I've told you in, I think in last session or before that, that this is IXL. So your the wire which you are using to make the coil will have certain withstanding voltage. If uh, more than that your voltage gets dropped, so it will lose its insulation, right? So you have to take care of that. Because of this, we need a self inductance. We need to know our self inductance, right? But here we cannot observe our output voltage, right? We know voltage across the coil. We know our mutual inductance. We know our self inductance. We know the coupling coefficient also. But what if I want to see the variation of my output voltage? Can we see from here? No. So for that, within this circuit, there is within this simulation only, there is an option known as Maxwell circuit, right? So how to use that? I will just let you know. So actually, it is also known as giving external excitation to your winding. Okay, so we will learn how to give external excitation and we will see how we can analyze our output voltage, right? From see, this is just a coil. So for analyzing output voltage, you need circuit, right? So we will see how we can make that circuit in Ansys within this option only. Okay, so I'll just switch to what we have discussed in the morning first. So in the morning, we discussed this circuit, right? I told you for if I want to know the variation of my output voltage, or if I want to know what is my output voltage, I need a circuit, right? So this will be that circuit which we will be making in Ansys Maxwell circuit. So how to do that? We will just discuss this in few minutes, but let's just revise this portion because now we will use this portion. Okay. So I told you this above one is the block diagram for wireless power transfer, right? So you guys told me that there are second year student also, and till now power electronics and all have not been discussed for them, right? So for now, don't concentrate on the power electronics elements. Don't concentrate on the power electronics converters. I'll just tell you in short what these converters do, and then how we have derived to this circuit. Okay, how we have derived the equivalent circuit that you are seeing here. So first thing is, you have your grid, we have your PFC. PFC does your power factor correction. So this is a whole uh, different topic. So we are not discussing these things, okay? Then comes your inverter. What your inverter do? The output of this PFC is DC, right? So what your inverter do? For wireless power transfer, what we need? High frequency AC we need, right? So this inverter converts DC to AC. So output of this inverter will be AC, right? This gets transferred here by flux linkage. Then what your rectifier do? It converts your AC to DC. And this is your DC load. Okay. So I told you that only on this part we will concentrate first. Okay. So we have seen that we got DC, then inverter, then your high frequency coils, rectifier, and load. So now you can see we have discussed this in the morning also, but I'm repeating myself. You can see for wireless power transfer, we need a coil, right? And that coil will have certain inductance, right? And because of that inductance, the VA rating of your system will increase, right? Because of this inductance, there comes resistance plus reactance, right? So because of that, the VA rating of your circuit will increase. So to avoid that, what we do is we make our circuit to work at resonance. So how we do that? For resonance, the first condition is Xc is equals to XL. So coil we already have. What we'll put extra? Capacitors here. So we will put capacitor here such that it's such that Xc will become equals to XL, right? So this is the condition for resonance. And you know at resonance, your circuit become purely resistive, right? So this will this will reduce the VA rating for your system, right? So through this, we have derived the condition for resonant frequency. Omega is equals to under root of LC, right? So this is the frequency at which you need to switch your converter so that your circuit will operate at resonance. Understood? So this is so now to get output voltage, to see its variation or to get output voltage at one particular point, this this is the circuit that we are simulating in Ansys, right? Till now we have just seen how to make a coil and all, but now we will see how to simulate this circuit in Ansys. Okay, so we are not using see, in Ansys, there are two options. One is Simplorer, where you can operate in closed loop also and in open loop also. And you can use switches and all like MOSFET, IGBT. But the option we are using is known as Maxwell circuit. Here, you cannot use switches and you cannot give like a closed loop and all. You just have to you can just simulate the equivalent circuit consisting of only sources and passive elements, right? No switches. Fine. So let's see how we can do this. So I told you that we have two options in Ansys uh, for simulating the circuit. Fine. So one is this twin builder. Now in latest version we call it Simplorer. So Simplorer and twin builder are one and the same thing. Here also you can simulate your circuit, and here what you do is you can use switches also like MOSFET and IGBT. But we are not doing this. This is something like advanced thing. So for now you don't need to know this. Okay. So if you just want to see the output variation, you can just do it by using sources and passive elements. So within this circuit, we will do that. So the first thing to do is change your winding from current to external. Okay. Then go to excitation. Go to excitation. Right click it. External circuit. Edit external circuit. Then winding 1 and 2 will be selected here. Then create circuit. So when you will click on create circuit, this will open on its own. So this is your primary coil winding 1, and the winding 2 is your secondary coil. So just now we have seen the equivalent circuit, right? With AC source and DC load. So that we will make from this coil. So this coil will have the same inductance as your as the coils that you have simulated. Okay. So these coils are signifying that coils only that you have simulated in Ansys. Okay. So these have certain option. Control R. With control R, you can rotate the coil. Okay. You know dot convention, right? So do you guys know dot conventions? Okay, fine. I think this part people have already told. Like in 11th, 12th only we learn this, right? Um, Yeah. So just flip this coil. Then what was the first thing? AC source, right? So you can see a dialog component library here, right? On the right hand side, you will see component library. So from here, you can choose source, right? So sine, we need sinusoidal source, right? So we will select this. To select that, just double click on it and pull it in your screen, right? Where you want to place, just pull it. Then the next thing was to make the circuit operate in resonance. What we need? Capacitors, right? So from passive elements, you can get capacitors. One, and this is the second capacitor. And now what is left? Load. So for load, we are using resistive load. Drag and drop. Just you have to drag that and drop here. Okay? Understood? So whatever elements you need from your component library, you can just drag it from here and you can drop on your screen. Okay? Fine. Now we will just connect it. Control R I have used for rotation. For connecting, just join 2 points. No wires and all you have to select, just join the 2 points. Okay. So now your circuit is ready. This is the circuit that we have just seen. So you know how you have got this circuit, right? You can just adjust the name and all. Okay, fine. So you guys understood how we have made this circuit? I have just discussed this, how we got this equivalent circuit, that you understood, right? And how
Yes,
we
ma'am.
made, how we simulated this circuit here, that you understood?
Yes, ma'am.
Okay, good. So now for measuring voltage and current, you need certain meters, right? So for measuring voltage, you need voltmeter, and for measuring current, you need ammeter, right? So we will take that from here as well. I think. So if your component library is not visible from view, select component library. Okay. So we need voltmeter and we need ammeter, right? So how to connect voltmeter and ammeter, you know? So voltmeter is always connected in parallel and ammeter is connected in series, right? So this direction tells you what is the direction of the current. So you have to place it accordingly such that current will flow from this side. Okay. Space for ammeter. Just I'll just make some space for ammeter. Okay. Hmm. Now you can do it. This and now I'm just adjusting the components such that your ammeter fits. Okay. So this voltmeter will give you the output voltage here, right? So this ammeter will give you output current. This voltmeter 52 will give you output voltage. Ammeter 53 will give you output current. So if you want to see your output in input current and all, you can also place one ammeter here. Fine. So just be careful while placing the ammeter that the direction of current should be through this arrow. Okay.
Okay, ma'am.
Can you see it now clearly, the whole circuit?
Ma'am.
Hmm. Okay, fine. So now we will just change the value. So see, the coil inductance is not in our hands. Means it is in our hands, but it will come from the simulation, from your Ansys simulation, right? So the value of input that we will decide. So frequency is 85 kilohertz, right? And see here you just have to set two values. VA is peak amplitude of your source, right? So I'm setting it to 400 volt, and Vfric is the frequency that you need. So I told you in wireless charging of electric vehicle, mostly we keep 85 kilohertz. So that I've kept here. You can just change it from here also. K, then you just have to write 85 here. Okay. So from here you can change your unit also. So now it is 85 kilohertz, 400 volt. Apply. Okay. Right. See, for now, you don't know the inductance. You have not run your simulation, right? So you cannot give the value of your capacitors. For that, at least one time you need to run your simulation, right? To know the inductance and mutual inductance so that you can give your capacitors value. Why we need inductance to give the capacitor value? Because we want our circuit to operate at resonance, right? Just now I have told you. Okay,
Yes, ma'am.
fine. And depending on the power output you want, you can just select the output resistor, value, means load value, sorry. So depending on uh, how much power you want, you can select your load value. So I'm keeping as 30 ohm. So see, it's like mm, I told you in the morning that when if my output resistor is RL, the value of my load resistor is RL. So when for deriving equivalent circuit, when I bring it in front of rectifier, I use 8 upon pi square into RL. In the morning, we discussed this, right? If you guys remember, right? So through that only, I have derived this 30 ohm. So it is like 3.3 kilowatt. I got this 30 ohm value. Are you guys understanding? See, in the morning we discussed this. I don't think you remember. Okay. First we will see this, then we will see how this 30 ohm has come, right?
Okay, ma'am.
Or let's just first see that only, or you will get confused. I'll just stop sharing here. It's better to clear doubts at that time only, then you can just concentrate on other things, right? So in the morning, I told you that if if the if my output resistance is RL, for deriving this equivalent circuit, I need this resistor to be here, right? On the input side of rectifier, right? To get this circuit, right? So
Ma'am.
if the value of it is RL, the value of this resistor will become 8 upon pi square into RL, right? Because for we are not for deriving this equivalent circuit, we are not considering the converters, right? So the out for deriving this equivalent circuit, what we considered is the output voltage of inverter, which will be AC, this capacitor, this inductor coil, and then transmitter coil, this capacitor, and then here is one load resistor, right? So the value of this load resistors will be a resistor will be 8 upon pi square into RL. If RL is my output, is the value of my output load, right? So how this RL we get? RL is equals to P out square upon P out. So my output voltage is, and P out, I can consider anything. So I have considered it to be 3.3 kilowatt. So from here, what value you get?
$12.12. Hello, ma'am. 12 point.
48.48. No, 48.48.
What?
This is square.
Yes, ma'am. Yes, ma'am. Understood, ma'am.
Okay. If you will just do its 8 upon pi square, you will get some certain value as, I think it will be around 42 or something like that. Just do 8 upon pi square into RL. This is the value of RL. So actually here I have considered it to be 350, around that. What is the value of RL you get here? After doing 8 upon pi square, can anyone know? I don't have my calci. Okay, I'll just do one minute. 8 upon
9.29, ma'am.
39.29, right?
Yes, ma'am.
Okay. Should I cross check or it's fine?
Yes, ma'am. It's fine, ma'am.
Okay. So 39.29,
29.
right?
Yes, ma'am.
So this is how we get the value of our resistor. Understood? This resistor. Understood? You can keep put this value also.
Yes, ma'am.
Okay, but with a 30, actually you get correct 400 volt. So I have kept it as 30. Okay.
Okay, ma'am.
With this somewhat value will change, somewhat it will change. It's fine. So stop. Okay. So this is clear now. Then after this circuit will not work if you will not put ground here on both primary and secondary side. So how to do that? Draw ground, one here and second here. Okay. Draw
Okay, ma'am.
and then ground. Then from max schematic, go to Maxwell circuit, export netlist, what was the option? Netlist. Export netlist. Then you can name this anything. Just let's call it Maxwell circuit only. And then just save. Okay. But remember the location where you have placed this file, because you have to give this file in excitation. Okay. So
Okay, ma'am.
just we will just save this. Fine. Then
Yes, ma'am.
in excitation again, go to excitation, right click it, external circuit, edit external circuit, and import circuit netlist option. So in on desktop we saved that, right? Maxwell circuit, this file, right? So just select that file and open. So you can see here you will get here it will say that we have successfully imported our file. Okay. But I told you, for now, the value of this capacitor we have not given. Why? Because we have to run it once to know what is my inductance value. Depending on that only, we will give our capacitor value, right? So what we will do is, if you want to do parametric study, for now, uh, for just setting the value of capacitor, don't do parametric study. So just disable it for now. Just see, we need the value of inductor when your transmitter and your receiver coil is one above the other. Okay. So at just one point you need, then you can set it, and then you can calculate for sweep also. But for initially, when you want to set the capacitor value, I am just disabling this setup so that I will run it on just one point, that is when my transmitter and receiver coil are above each other at some air gap. Okay, at one point only. Okay, so for now it is 150. So just validation is done, then analyze. Let's see the progress. Okay, I think it's, yeah, simulation is completed. Then what we will do is we will go to our results, eddy current, then data table, and inductance we will see. So what we need is self-inductance, mutual inductance, and self-inductance of secondary coil. So this is the value, right? For what is the self-inductance of primary coil? L1 is 380.139 microhenry, right? Then what is your self-inductance of secondary coil? You can see it from here, right? 378.315 microhenry, right? And your mutual inductance is 69.1352, right? So this is done. Now we have to calculate the value of your capacitor, right? So this value we got from simulation, right? So I told you my frequency is 85 kilohertz. So I told you the formula to calculate capacitor value. It's omega is equals to 1 upon under root LC, right? So just substitute it. So for C, it will be like 1 upon 2 pi F square into L1, right? So this is the way to calculate capacitor value, you will just substitute all the value. But in Maxwell circuit, for making it operate at resonance, you have to give L1 minus M, this M, mutual inductance. So in real life, you will just give the self inductance, right? But in Maxwell circuit, to operate at resonance, you have to minus it from this M value. So just calculate what is the value of C1 that we are getting. F is equals to 85 kilohertz. L1 is 380.139 microhenry minus 69.1352 microhenry. So just tell me what value of capacitor that you are getting. Calculate it, please. 2 into
1.127 into 10 to the power of minus 14.
1.12.
7.
Tell me nanofarads. It will come somewhere like 15, means in that
10,
range, some nanofarads.
10 to the power of minus 14 I got, ma'am.
Let me just check answer. And 139 minus 69.1352 into 10 to the power minus 6. 11.27 nanofarad you will get. Right? Similarly, please calculate C2. L2 minus M. What C2 value we get?
11.445 nanofarad.
11.34 nanofarad.
45, ma'am.
Okay. Okay, you have kept all the. Okay, 45 is also good. Fine. So C1 is 12.27 nanofarad and C2 is 11.45 nanofarad. You understood now how we have calculated this? Through resonance condition, right? So we will just put this value in our simulation. This is something advanced thing, but because we had some time, that's why I'm discussing this. Okay. So we will go to our circuit. We'll change its value. What is C1? What was C1 that we calculated? 11.27, right? Just change from pico to
Yes, ma'am.
nanofarad. Apply. Okay. And C2? 11.45, right? Nanofarad. Okay, apply. Okay. So now you have made changes in your circuit, right? So every time you make some changes in your circuit, go again, you have to export the circuit. So go to Maxwell circuit, export it. You can just select the same name, this, and save. So that new circuit will get saved. Understood? So every time you make even a small change in your circuit, you have to export it. Okay? So that that change will get reflected. Fine? And then again, you have to import it also. So go to excitation, external circuit, edit external circuit, import circuit net list, Maxwell circuit, open. Okay. It is imported successfully. So you guys understood? Even
Ma'am,
if we
please
make
check the
small changes, we have to import and export it again. So you guys
ma'am, please
have
share the video.
what?
We are
Hello?
not seeing. We are seeing the. Hello, ma'am.
Huh.
Please share
Yes.
the laptop.
My screen is shared. I can see it on my iPad. I think with you only it is the issue. My screen
Okay,
is
ma'am.
shared, right? Mhm. Because I can see it on my iPad. So I know there is no issue with screen sharing. Only you are facing the issue, or other people also facing the same issue? Can you see my screen? Are you guys able to see my
Yes,
screen?
ma'am. Now it is.
Okay.
Yes, ma'am.
Okay.
It is now visible.
Okay. Okay. Fine. So, if you have missed that, I was telling you that when you are changing your capacitor value, you have seen this, how we can put our capacitor value. Just double click on the capacitor, put the value, change the unit, and OK. So after you have given your capacitor value, just again export it. So go to Maxwell circuit, export netlist, and you can select the same file that you have saved it, select it and save. So it will be that file will be replaced. Okay. So now one time you have replaced, you have exported. Now again you have to import the new file. So go to excitation, external winding, edit external circuit, import circuit netlist, select the circuit, open. It is imported successfully. Okay. So now again you can just validate it and see our parametric setup is disabled for now. We will see with parametric setup also. But for now we will just check on single value first if we are getting proper results. Okay.
Okay, ma'am.
So analyze. Okay. So yeah, it is completed. Your simulation is completed. So now to see output voltage, what you have to do is go to result. So first you have to see what is the name of my voltmeter. Output is voltmeter 52, right? Now go to results, create eddy current report, data table because only one value we are seeing, so no need to plot it. Then node voltage. Okay, so only one voltmeter is there. Therefore, you are seeing only one voltmeter here. And then select its magnitude. Node voltage, voltmeter, then magnitude, then no repeat. The simulation was on the I think the simulation was not properly done. I'll just again run it. It's fine. This is 5 kilohertz. This is fine. And voltmeter is connected properly, right? Yes, disconnected properly. Some random values should have come. That also it's not showing. Means that means there is no problem with the circuit. Simulation error is only there. Okay, let's just try it again. External circuit, edit external circuit. Hmm. The rest of the results are coming fine. Yes, 0.128. The rest of the results are fine. Okay. Hmm. Did I miss anything again? Let's say circuit is correct. Every values we have given. This is winding one, primary only, right? Let me see. That winding two is secondary only. Why it is not giving any values? Let's change our air gap and see. So this should not happen. Why it is giving, why I'm not getting any values? I'm not understanding. This is very, this is also correct. Okay, just, I don't know what is the issue with this, but I have one circuit that we have made. We will check for that. Okay. This is the same circuit. We will analyze on this circuit. Okay. Mm, this is in setup we have to do again. Well, it defines it occurs. Optometrics we will change. Analyzer. Hmm. This is the same circuit that we have drawn up. Maybe this there is a version difference. That's why I'm not getting the proper results. Okay, we will see here only. So this geometry was made in higher version, and now I'm using like 18 because that is what available. So maybe that's why I'm facing issue, but we will see. If we are not getting here also, then that is the issue. Version maybe. Yeah, here we are getting. Okay. So this is the circuit. We will just, this is the same circuit that we have drawn. We will just check its inductance and mutual inductance. Around same we have, right? 67.1.17. And this is 68.84. 9, 11.87, 11.25. So we will just change the value and export it again. Okay. Change the value of capacitor. 11.87 nanofarad. Okay. 11.45. Maxwell circuit export netlist. Excitation again. Edit external circuit. Open that file. Imported. Then this time we will just run the optimetrics also. So just we will add the parametric study 100 to 250, no, 40 steps is fine. So that we will get some value. Yes. Okay. The same thing that we did in the circuit, that is only what we are doing here. The simulation is running. Just wait. It will take 5 minutes to run. So just wait. One reason that I feel is the issue is my circuit is made in the higher version, and this Maxwell circuit we made in lower version, right? So maybe that is, I feel was one of the issue, because both of this circuit are made in higher version. I'm not getting error here. So I feel that is one of the issue, but let's see, because rest all of the things are the same. Okay.
Okay, ma'am.
Maybe version issue is the problem. That's why I'm showing you the result where both my circuit and my geometry are both uh, simulated in one version only. Okay. So I'll show you when you will follow the same step, you will not get this error. Okay. So don't worry about this, because you will make all in one version, because there was some version differentiation. I think that is the issue, that we were not getting results there. Okay. So till this simulation is running, if you guys have any doubt or like any questions, uh, related to anything, transformer, inductor, or coil, whatever we have discussed till today, if you guys have any doubt in that, you can ask me, because today is like the last class. after this class also you can WhatsApp or email me your doubts. I'll try to solve it there on there also. But like now we are just meeting face to face, so it will be easy to communicate. So whatever doubt you have, you can just ask me now, because we have time till this simulation is running. You guys understood everything that we have discussed till now? So if I ask you to draw any geometry, you like by giving dimensions and all, and if I ask you to analyze things, will you be able to do it? Will
Yes,
you be
ma'am.
able to do it? Good. So I'm asking this question because I'm designing one assignment for you guys. So you have to submit it to Rakesh sir. So he will tell you the last bit, everything related to submission. He will tell you. But by tomorrow, I'll give you one assignment thing. There you have to draw certain geometries. I'll give you the dimension and all, and what to analyze. That also I'll tell you. But you have to do it on your own, right?
Okay,
If you
ma'am.
guys have doubt, you can WhatsApp me the doubts. Uh, but that you have to actually have to. I guess you have to submit. Rakesh sir, they have to submit the assignment, right?
Yes, madam. They have to submit.
Yeah. So
I'll
uh,
circulate that assignment.
what?
I'll circulate that assignment. They have to submit also.
Yes. Yeah. So in the while doing the assignments, if you have any doubt, uh, either email or WhatsApp. I think Vamshi has my number, and you can just circulate it in group, and I will clear your doubt at that time also. Okay. So don't worry, it will not be that difficult. Everything that you need will be written there. What? Sorry, there is network issue. I'm not being able to hear you properly. Hello? Okay, our simulation is completed, so just we will analyze the results. First, rectangular plot, air gap. So first we will analyze how your output voltage looks. So what is the voltmeter number for my output voltage? It's 45, right? Eddy current, rectangular plot, air gap, node voltage, 45, and magnitude. Some parts have lost. In data table, you will see this. Sometimes it happens. This is because you don't take your mesh uh, properly, na? So sometimes at some points your result don't converge. So it happens sometime, but it's fine. You can just rerun your simulation and see. Magnitude. So this voltmeter 45 is your output voltage, right? So you can see how your output voltage is varying with respect to your air gap, right? So if you want to analyze it for uh, how my output voltage is varying with respect to x distance, y distance, that also you can analyze. Understood? So from here, you can analyze your output voltage, your output current, output power. Mostly don't trust this value, just normalize this, because you are making equivalent circuit, you are not making like all with your converters and all. So like variation will be same. So how the variation is looking, it will be same, but values they might not be correct. Okay. So usually instead of putting values, you just normalize it, right? And just you can show the variation. Understood? Fine.
Yes, ma'am.
So with this, we have completed all our objectives. So if you guys don't have any doubt, this workshop will end here. All the objectives have completed, and extra objective also uh, I just discussed with you. See, in the manual that I have circulated, there are some things that is different from what we have discussed. So I'll rectify that, and I will add this objective also there. So you don't need to worry about your manual. So in manual, all the results will also be added now because we have drawn all the simulations. So I have results for everything. So I'll add that results also. So I'll just rectify the manual and will send it to Rakesh sir by this week or so. Then you can see from there. Okay. Whatever doubt, even steps also, what we followed, that I'll write. Okay. Some steps I have written in general form. So now it will be more specific, right?
Okay, ma'am.
So with this, we have completed our session. Hello, Rakesh sir.
Yeah,
Uh,
yes, madam.
If the students don't have any doubt, I've completed
Wait
my
for 5 minutes,
object.
madam.
Yeah.
You have wait for 5 minutes. Students, meanwhile, if you have any doubts, you can ask for 5 minutes. We have 5 minutes to ask doubts. Any participants?
Hello, good evening, madam. Myself, Dr. Bukkeva Singh, head of the department.
Good
Madam,
evening, sir.
in this wireless charging, it is in Ansys, it is possible for the misalignment analysis, madam.
Yes, it is possible. That is what I was telling. We can analyze it for different air gap as well as for misalignment. So for analyzing it for misalignment, I'll just share my screen. So for analyzing it for misalignment, uh, op- we have to parameterize that distance also. So here, I have uh, parameterized at x distance and y distance, right? So if I'll change this, for now it is 0 0. So 0 0 means my transmitter and receiver coil are one above the other. So if I change it, you will see that my receiver coil will be displaced in x direction. Similarly, if I'll change my y distance, you will see that it is displaced in y direction. So here in optometrics, you have to select that as your parameter. Instead of air gap, you can select x distance and y distance as your parameter. And through this, you can analyze the misalignment. Okay.
Yes, thank you, madam. Madam, if it is total design is over, how much time it takes to get the result, madam, for running time?
Uh, like it depends how many parameters are there. Uh, that you want to analyze. So if you have taken it, see here only five swipe was there. So if you are taking like 100 or more, so it will take a lot of time to simulate. But with this solid coil, it will take less time. But if you will make a wound coil, it will take a lot of time to simulate.
One coil means
So
circular coil for polygonal hexagon.
Yes, circular coil means in, see, if you made in this fashion, it will take less time. But if you will make in this fashion, I'll just show you. So this fashion, like in number of turns as a spiral form, right? So it will take more time.
Okay.
So usually we make in this, even see, circular coil also we can make in solid form, that I have taught in last class, and in spiral form also. So solid form takes less time to simulate. The spiral form takes a lot of time to simulate.
Okay, madam. Thank you, madam.
Yeah.
Hello, ma'am.
Yeah,
And
any part?
angular misalignment is also possible, ma'am, in this similar.
In see, angular misalignment is possible, right? But in I work in wireless charging of electric vehicle. I told you their angular misalign a thing like angular misalignment uh, is not that popular. Okay, so angular misalignment I usually don't analyze. I just analyze X misalignment, Y misalignment, and air gap. But it's not like we cannot do it. Okay, so you have to parameterize that also then. So you have to just
Okay, ma'am.
copy paste it, and then you have to rotate, you have to give some rotation, and then have to parameterize it. But if you want to analyze it for some other application also.
Okay, ma'am. Thank you, ma'am.
Anything else?
Any more doubts from the participants? So I welcome all the participants to give some feedback. At least few participants can come forward for the feedback. If you don't have any doubts, then we'll go for the feedback session.
Okay, sir.
Yeah, carry on with the feedback. Anybody can give feedback. So you have attended 12-day sessions, right? How the sessions were there? You can give some feedback. You can give some briefly feedback. It's okay.
Hello, ma'am.
Yeah.
Thank you, ma'am, for teaching this software to us from my side, ma'am. It is a great opportunity for us, ma'am, to
It
learn
was
this
a
software.
it was a great opportunity for me as well, because this is the first time I teaching a class of 40-50 students. And if it would have been like a face to face, I would have enjoyed it more, because I would have, uh, in that case, I would have been able to see you guys and would have like figure out if you are understanding or not. In online, it becomes difficult, but I hope I've given justice to this Ansys software thing.
Yes, ma'am. Yes, ma'am. Everything.
Yeah, any more participants? Feedback. Vamshi, you can go ahead.
Yes, sure. Good evening, everyone. I'm Vamshi, the chair of the IEEE student branch at RGK Basar. It's a great pleasure to speak at the conclusion of the World Ansys workshop. This was the first event under our newly formed IEEE student branch. I'm happy to see that it was a meaningful and successful beginning with over 60 plus participants from the India. this workshop gave us a hands-on exposure to the Ansys software, especially focusing on the wireless charging system for the electrical vehicles. I would sincerely thank our Honorable Vice Chancellor, Professor A. Govardhan sir, for his encouragement and support. I thank Professor E. Muralidharan sir, OSD of the RGK Department, his continuous guidance. And I thank Dr. Bhav Singh sir, head of the Department of Electrical Engineering, for his consistent support. And I thank you, ma'am, Miss Utkarsha madam, for delivering excellent technical session for us. And I finally thank Dr. Naman Rakesh sir, our faculty counselor, for mentoring and guiding us throughout the session. I finally thank all the participants for actively engaging in this session. Your interest and involvement made this session successful. Thank you and best wishes to all. Sir, can you speak some words, sir? Naman?
Yeah, thank you, Vamshi. So, good evening, all. So, I welcome all the participants to this valedictory session, and I thank Honorable Vice Chancellors Professor A. Govardhan sir, respected AO and OST Professor E. Muralidharan sir, and today's workshop speaker Ms. Utkarsha Madam, Deans, HODs, and Mr. Dr. Bhav Singh sir, HOD Triple E, and faculty staff and all the participants and coordinators and volunteers of IEEE student branch at RGKT Basar. So a warm welcome to this valedictory session of 12 days workshop on Ansys software in online mode. Like I said during the inauguration also, it's our first event under IEEE student branch after its recent formation. So soon we'll have a in a bigger way, we'll have the inauguration in our university also. So but the activities we can go ahead with the activities. That's what we got the confirmation from IEEE student branch. So we are conducting the activities. We'll see multiple events under student branch in the future also. So even I too observed that out of 200 registrations, so more than 50 students or 50 participants have participated actively, and the remaining might have followed the recorded videos also at later stage. So the content like 2D and 3D geometry, excitation, modeling, simulation, wireless, inductive power transfer, and so on, had delivered successfully from the basic level to understand to all the participants by the speaker. And unlike the other workshops, it is unique. Like I can say, it is unique because it has lecture notes as a manuals, and daily lectures, live lecture sessions are there, and also video recordings, and also assignments. So this kind of lectures generally we can see in SPIAM NPTEL courses only. There also will have lectures, video recordings, assignments. So kind of things will be there. All these four contents are available. So four quadrant teaching we can see in this lecture, in this workshop. So after this workshop, we can directly even include this course in our lab curriculum, because all the content is available with us. Now we can include directly all these 12 days experiments or 12 days sessions as a 12 experiments in our lab, simulation lab, or separate new lab also, because all the content is available with us. So once again, I'd like to thank our Honorable Vice Chancellor sir for his constant support and encouragement, for the initiation of IEEE student branch at our university, and for his guidance and the permissions to organize this workshop under student branch activities. I thank IEEE Hyderabad section officials, region and head office officials for the approval to this branch our university. I thank AO and OST for his time and quickly approvals and permissions. I thank deans, HODs, all the supporting section heads and their staff, HOD Electrical Engineering, faculty, staff. And I would like to thank our two professional members, Dr. Naganjanil sir and Srijana madam. And I would like to thank student chair, Mr. G. Vamchi, who has coordinated successfully his first event under student branch activities. And this event or this workshop completely coordinated by him only. I'll leave it to him because I would like to encourage him. I would like to see him how he will coordinate. So he has successfully coordinated this workshop, even though it is first time for him. And It's time to say a big thanks to our workshop speakers, Miss Utkarsha Madam, for spending her valuable time to share her knowledge for this workshop through the lectures, recordings, manuals preparations, and assignments. You have taught this in these workshops. You have taught almost semester content, Madam. So once again, I would like to thank you. And like I said, all the sessions might have enjoyed by the participants, and it has reached to the participants in a good way. Thank you, madam.
Thank you, sir. Thank you, sir, for
Even
giving me
later,
this opportunity.
actually, from this, yeah, thank you, madam. Later, we have identified few participants. From that part, with that participants, will conduct one more workshop in our university face to face, madam.
Oh, thank you, sir.
Yeah, yeah. Thank you.
Thank you.
So
Thank you
next,
for
I welcome Bowsing sir to speak few words.
Good evening, all. Thank you, Vamsi, student chapter IEEE. Respected Honorable Vice Chancellor, sir, Professor A. Govardhan Garu, respected AO and OSD, Professor E. Muralidharan Garu, and workshop coordinator, Dr. Naman Rakesh sir, and IEEE chapter Vamsi. So I congratulate all the participants for this successful completing of this workshop under the IEEE chapter, student branch chapter. So same thing, your encouragement, same thing, your participation is required for the further any conducting of the workshop under the IEEE branch as well as the electrical department. So I hope same continuation is expecting for the other FDP also. Thank you, sir. Thank you all.
Yeah. So Vamshi, all the participants, I would like to thank all the participants, and let us turn on the video once so that we'll have one screenshot as a closing. Vamshi, you can take one screenshot that all the participants can turn on. Vamshi, you can turn on your video first. Yeah. Is it okay, Vamshi?
yes, sir, it done. So 1 minute.
Yeah, I could see Jakir sir also. Thank you for participating, sir. Jakir sir.
Yes, sir, done, sir.
It's okay, now, Vamshi?
Yes, sir, it's done.
Yeah, okay. Thank you, madam.
Thank you, sir.
Thank you, ma'am.
Yeah, thank you all
Thank
the
you.
participants. Thank you, sir. Now we can leave the session.
Thank you, ma'am.
Thank you. Thank you, everyone.